All right, everybody, here we are, Module 1, Part 2. So it should say B on there. Put this in there. What page are we on? 60? 16? I was about, how did we get all the way to 60? 16. Oh, sound. Okay. Motion of the oceans. We're still very general here as far as the ocean. Remember we talked about salinity last time. Now we're going to be looking at motion and wind and things like this. All right, so first question is, why does ocean water look blue? That's not really a question up there, is it? Why ocean water looks blue?
Yeah,
It's not a complete sentence or something. Sorry about that. But we're seeing a beautiful picture of the blue ocean right there. So we're going to fill in, here we go, we're going to see some refraction and reflection of water, some light and absorption of light and reflected blue. I'll watch a little small video here in just a second. So part of the reason here is the ocean appears blue because the way that light is absorbed by seawater. So we know that seawater is dense because it's salty, right? All water's fairly dense because it is heavy, but we're going to see seawater with the salt in there is really dense. So we're going to see that the light is absorbed at different wavelengths at different depths in the ocean. So look which one goes the deepest. That would be blue, right? So the blue lasts longer, if you will. The blue light lasts longer in the water. Okay, the rest of it gets reflected away. So here we're going to fill in some blanks here. Ready? Light has different wavelengths, and the ocean water is most transparent. That's the way of saying it. It goes the deepest. Most transparent to blue light frequency. The deeper the water, the other colors cannot penetrate, so the bluer the ocean appears. And furthermore, it is true that the reflection of the blue sky, reflecting off of the water, does make a difference there. Oops, I'm sorry. I'll go back to that. Did y'all need those still? It's just not 100% due to reflection. There's also that refraction situation. And everybody remembers from grade school the colors of the rainbow. What is it? Roy G. Biv. Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. Always in that order. Remember, the backward rainbow goes backward colors if you have a double rainbow. All right, so notice the picture here. You can see how that blue is penetrating deeper. We're actually showing how far. I believe that is, does it tell us? This is meters, so that must be feet. So 37.6 meters, 125 feet. That's about right. So look, the red really doesn't go very far at all. Okay, so we're going to watch this cute little video here of this guy in the boat. It's very short. Oops, that was really short. And here we go.
Why is the ocean blue? 'Cause ocean water reflects blue color of the sky. You are right, but not completely. The main reason for oceans to be blue is the way water molecules absorb and scatter the colors of sunlight. Sunlight has 7 visible colors. They are red, orange, yellow, green, blue, indigo, and violet. Yeah, I saw them in a rainbow. Now, when sunlight falls on the ocean, it passes deep into the water. Here, red, orange, yellow, and green colors of sunlight are absorbed more strongly by water molecules, while blue, indigo, and violet colors are not absorbed much. Instead, they are scattered, making the ocean appear blue to us. However, as the blue shades penetrate deeper into the ocean, eventually they also get absorbed. Hence, at greater depths, the ocean is completely dark.
All right, there you go. Very informative. Keep on going. Okay, different types of plankton will also reflect light, giving off a turquoise color. Okay, plankton. Have we talked about the word plankton yet? Have you heard of plankton? What does it mean?
Little
organisms in the water. Okay, that is true, but not exactly. One thing I want you to think of every time you hear the word plankton, not that little critter from the cartoon, right? Anything that is anything that cannot fight the current is plankton. So anything that floats. So if it floats, it's plankton. That even refers to a piece of wood floating in the ocean, floating in a lake. It's considered plankton because it's floating. Okay, so that's the technical thing right there. We're going to look specifically in this class at types of plankton that are found in the ocean. Have you ever heard of flotsam and jetsam? Nobody seen Little Mermaid? I'm talking about the original cartoon. There were those two little eel creatures, and they were named Flotsam and Jetsam. Yeah. Well, it's funny because Flotsam and Jetsam refers to the plankton. So flotsam is floating things that are from living things, so or maybe even still alive, like planktonic creatures, and jetsam is stuff that's floating that's not alive, logs, trash, things like that. All right, so here's a picture of some plankton that tend to be bluish in color. We're going to spend a lot of time on the microorganisms of the ocean. Pretty soon I'll be bringing microscopes for y'all to check these out and look at them and draw them all and all that kind of thing like that. But they'll end up causing, not only do they reflect something like this, an ocean scene where we see the blue. That's a Caribbean, from the Caribbean. Y'all have been to the Caribbean? No, not down even to Mexico?
Oh, wait, is it Caribbean and then by Louisville?
Yes, I think so. That's the top of the Caribbean, right. So you've been to Puerto Rico? Yeah. So if you're on the eastern side of Mexico, Puerto Vallarta, Cancun, that's all considered the Caribbean or Caribbean. Very blue, very blue. You can see down to the ocean floor, right? You say, oh, look, it's like 5 feet deep. No, it's like 35 feet deep. And it looks like it's right there, but it's not, okay? But so we have the light absorption, we have the light reflection from the sky, we have the plankton. We even have plankton that at night, they're so blue that you can stir up the water and they glow. It's pretty awesome, okay. Let's talk about pressure now. Ocean water pressure is critical for dissolving gases in the water. It's important that gases get dissolved into the water so that creatures who live there can actually have oxygen to breathe. So we need pressure to squeeze the oxygen from the atmosphere and get it into to the ocean. It can change very rapidly, mostly depending upon depth, how deep you go in the ocean. Y'all already know all that. So for every 10 meters of depth, I think this is a blank you're supposed to fill in, but I don't think I have it worded the same way. So for every 10 meters of depth, that's 33 feet, there's 1 atmosphere of pressure is added. So I think your top blank might be what is the pounds per square inch at the surface or on land, right down at the ocean, is 1.
Okay, so
1 atmosphere. All right, in fact, that's where we come up with that whole deal, was down at the ocean level, we come up with the air, this is the air pressure, the atmospheric pressure, okay? The higher you go, the lower the pressure gets. That's the whole deal about, oh, I can't believe I keep forgetting to put the book for this class in here. I have last year's A&P book. So I don't have my book, I'm sorry, so I can't read what the order of the blanks is.
oh, you're in this book?
Yeah, I can't, I should have fixed that. I've been out of town all weekend, so. Labor Day comes on a bad time. Okay, so as we go deeper, the pressure becomes more intense, right? We already knew that. You know that just intuitively. All right, so for instance, we're at 1 atmosphere at the surface. Okay, that's called sea level, right? So the coast of Texas would be sea level. As we get to Austin, we're a little higher than sea level. Our atmospheric pressure is a little less than 1. And then as we get deeper and deeper, we get to the atmospheres right here. We can see right here the gas volume. Notice what's happening. If I have, let's say I have a balloon, and I'm able to push it down into the depths of the ocean and not float back up or whatever, it's going to squeeze down inside. The pressure on the outside of the balloon is going to be greater, so the stuff on the inside will shrink up, okay? And this is important when it comes to marine biology because we have creatures that live in the ocean, and they have to be able to withstand the pressure, all right? So if we look here, we look at something called bars or millibars. It's just another way of measuring pressure. Sometimes we measure it in millimeters of mercury, atmospheric pressures, and here we're looking at something called bars. Is there something in your book that refers to bars? Are you supposed to draw something?
No.
Okay, cool. All right, so so the idea being that as we go farther down, greater and greater pressure being pushed. Y'all have been to the bottom of a swimming pool, yeah? And your ears feel funny and that kind of thing. And was it y'all I was telling about the movie I watched about the deep divers?
Mm-hmm.
Yeah. So the pressure gets to them as well. So they have to be able to they said that their lungs, you know, they have to take this giant breath, of course, right? But their lungs end up down the pressure, get as big as your fist. I mean, very tiny. And they're still holding their breath, you know, they still have to survive down. I know these people are crazy. But that pressure and then, of course, time is the thing that's working against those people. All right, this is a little bit of a weird picture. It's kind of showing those, like this, if this were our balloon, all the way over to the right, if that were our balloon, it would squeeze down like this. So you notice here, look at this middle picture of the rectangles, right? So it's full on both sides here, these two rectangles. As we go down, notice the one to the right, those rectangles all stay the same. That's just showing that mass of the thing is the same. Nothing's being taken away from the mass of the object. But the pressure affecting that mass of the object, if I had a piston, I would be pushing it up like that. Okay, squeezing it like that. And this is just showing our atmospheres in gauge and absolute. So if you ever do go scuba diving, you have a couple of gauges. One of the gauges tells you how much oxygen's in your tank. Another gauge tells you how deep, I think it usually has a watch. It tells you how deep you're going. And depending on how you're rated or how you've been trained, you can't go beyond a certain depth. Like I scuba dived once and I was rated to 30 feet, which is not very deep, you know. And that's because I learned in a pool before they took us out to the ocean. And the pool was only 12 feet deep. And apparently 12 feet deep rates you for 30 feet in the ocean or something like that. Okay, but it has to do with your body being able to withhold the pressure, withstand the pressure. All right, so we're going to see here when we start talking about the animals, the ones that have a more structured body type with bones, for instance, bony fish and things like this, will not be in the deepest depths because they can't take the pressure, all right? But other creatures down here who are floppy and don't have as many internal structures like bones, they can actually take more pressure and they can sort of take on the shape of whatever they're being squished into. Now, there are certain fish, including bony fish, that do live in great depths. You've probably heard of the one called the blobfish, right? Well, eventually when we can talk about the deep ocean, we'll talk about the blobfish. When we first found it, we thought it was fake, you know, we didn't know what was going on. But what we decided later was that it was a deep ocean creature and it got it got too high and the pressure wasn't enough. It'd be like us going into space without a spacesuit. It just sort of popped like that, okay? Because the pressure was off of it.
I was going to say that there's the ones that are down there, if you bring most of the animals off the bottom, they completely change shape.
They pop like a piece of popcorn. That's the blobfish. It changed its shape. So we have an idea of what it probably looks like when it's not, when it is under the pressure. It looks like a normal fish, okay? So we're going to watch this really fun, I think it's a TED video, right? TED Ed, and it's going to, I don't know if it's the blobfish. I don't know if he mentions if it's a blobfish, but it's something similar. I still have to click it, sorry. All right, here we go.
Sometimes, when a fish is reeled up to the surface, it will appear inflated, with its eyes bulging out of their sockets and its stomach projecting out of its mouth, as if it's been blown up like a balloon. This type of bodily damage, caused by rapid changes in pressure, is called barotrauma. Under the sea, pressure increases by 14.7 pounds per square inch for every 33-foot increase in depth. So take the yellow eye rockfish, which can live as deep as 1,800 feet, where there's over 800 pounds of pressure on every square inch. That's equivalent to the weight of a polar bear balancing on a quarter. Now, Boyle's gas law states that the volume of a gas is inversely related to pressure. So, any air-filled spaces like a rockfish's swim bladder or human lungs will compress as they descend deeper and expand as they ascend. After a fish bites a fisherman's hook and is quickly reeled up to the surface, the air in its swim bladder begins to expand. Its rapid expansion actually forces the fish's stomach out of its mouth, while the increased internal pressure pushes its eyes out of their sockets, a condition called exophthalmia. Sometimes rockfish eyes will even have a crystallized appearance from corneal emphysemas, little gas bubbles that build up inside the cornea. Thankfully, a scuba diver doesn't have a closed swim bladder to worry about. A diver can regulate pressure in her lungs by breathing out as she ascends, but must be wary of other laws of physics that are at play under the sea. Henry's law states that the amount of a gas that dissolves in a liquid is proportional to its partial pressure. The air a diver breathes is 78% nitrogen. At a higher pressure under the sea, the nitrogen from the air in a scuba tank diffuses into a diver's tissues in greater concentrations than it would on land. If the diver ascends too quickly, this built-up nitrogen can come out of solution and form microbubbles in her tissues, blood, and joints, causing decompression sickness, aka the bends. This is similar to the fizz of carbon dioxide coming out of your soda. Gas comes out of solution when the pressure is released, but for a diver, the bubbles cause severe pain and sometimes even death. Divers avoid falling victim to the bends by rising slowly and taking breaks along the way, called decompression stops, so the gas has time to diffuse back out of their tissues and to be released through their breath. Just as a diver needs decompression, for a fish to recover, it needs recompression, which can be accomplished by putting it back in the sea. But that doesn't mean fish should just be tossed overboard. An inflated body will float and get scooped up by a hungry sea lion or pecked at by seagulls. There's a common myth that piercing its stomach with a needle will let air escape, allowing the fish to swim back down on its own. But that is one balloon that shouldn't be popped. To return a fish properly to its habitat, fishermen can use a descending device instead, to lower it on a fishing line and release it at the right depth. As it heads home and recompression reduces gas volume, its eyes can return to their sockets and heal, and its stomach can move back into place. This fish will live to see another day, once more free to swim, eat, reproduce, and replenish the population.
Have eye damage or something though, right? Yeah. So, so those people that do the free diving, so it was really making an impression on me. Those folks, they don't have a tank of air on them. All right, so they don't have that decompression problem. They just have whatever was in their lungs to start with, and therefore they don't suffer from the bends because of that. The bends really comes if you have that nitrogen from a air tank that causes that. All right, ocean motion. What causes all this motion? There's a couple of things. Can you think of something? What causes waves to form in the ocean? Wind, that's one of them.
The moon.
Moon, tides, that's another one of them. Anybody else? We'll find another important one. Here we go. Global wind patterns. That's number one you're going to write down. Global wind patterns and the word gyres. Some people pronounce it gyres, but gyres are sort of little, I don't know, current things that form from the wind blowing on there. This is the one y'all missed. It's called the Coriolis effect. Who remembers Coriolis? Do you remember what that means? If you took physical science, you would have covered Coriolis effect. Do you remember? It has to do with the globe spins on its axis. We're moving, right? We're moving in a circle. We're spinning. And because of that, we have water. Think about if you stir a bowl and the water's going to keep going, right? All right, so that's Coriolis. We're going to see what that does. Currents and waves. That has a couple things that has to do with the wind, Coriolis, and temperature. You know, hot and cold, rising, and that kind of thing. Number 4, tides. Someone's always said the moon. That's the moon coming into play there. Okay. And then vertical motion and something called overturn. Okay, vertical motion going up and down in the water column. That is accomplished by creatures and accomplished by temperature changes. And we'll see how overturn in particular has to do with temperature changes. We'll study it here on sort of on a smaller basis, like a pond or something like that. Okay, but it's critical that we have motion in water sources, because you know stagnant water's not good. Yeah, I just came from a lake trip. We were at Lake LBJ and Lake Travis. We went to two lakes, and recently in Lake LBJ, somebody encountered an amoeba in the water, and it got into the kid's brain, and he died from it. So in stagnant water, amoeba will be living in there. So as long as the water's nice and moving, okay, it keeps things from like growing in large numbers, bad things from growing in large numbers. All right, everybody got their 5 things written down here? All right, the wind. The wind is created when the sun heats the air, and the air rises, causing cold air to sink. And as that motion's coming, we have a wind breeze blowing. So wind moves up and cools, then drops back down. And the turning of the earth also affects the direction. So we're going to see here on the globe, we're going to see those little circles coming around there. Notice how they're in like little quadrants. The equator is very influential because, as you know, the tilt of the earth are very fortunate for us. You may have noticed our tilt is changing just a little bit. If you notice, the shadows are coming in at a little different angle now. We still have plenty hot temperatures out there, but pretty soon, because the tilt, we're going to tilt away and we will cool off. We have to cool off because of the tilt of the earth. But if you're living at the equator, you tend to be facing the sun the same all year round. So the temperature at the equator tends to stay the same. Therefore, since it's warm, let's say it's warm at the equator, we're going to have winds that are building from the equator and going up, and winds that are building from the equator and going down, moving away from the equator, rising and settling down like that, okay? And so that equator has a lot to do with it. Remember, it's an imaginary line that we draw there. So what's a gyre? A gyre is a large, mostly circular system of surface currents driven by the wind and affected by the Coriolis effect. The picture here, it shows those giant circles. You can see the globe. Notice there's a giant one right here to the west coast of America, over by California. Alaska's up there. Hawaii's right in the middle. Big giant gyre going around there. So we have these main large gyres, and then we have smaller ones, kind of satellite ones, if you will. All right, another video to explain this.
In 1992, a cargo ship carrying bath toys got caught in a storm. Shipping containers washed overboard, and the waves swept 28,000 rubber ducks and other toys into the North Pacific. But they didn't stick together. Quite the opposite. The ducks have since washed up all over the world, and researchers have used their paths and are driven by a range of sources: the wind, tides, changes in water density, and the rotation of the Earth. The topography of the ocean floor and the shoreline modifies those motions, causing currents to speed up, slow down, or change direction. Ocean currents fall into two main categories: surface currents and deep ocean currents. Surface currents control the motion of the top 10% of the ocean's water, while deep ocean currents mobilize the other 90%. Though they're different causes, surface and deep ocean currents influence each other in an intricate dance that keeps the entire ocean moving. Near the shore, surface currents are driven by both the wind and tides, which draw water back and forth as the water level falls and rises. Meanwhile, in the open ocean, wind is the major force behind surface currents. As wind blows over the ocean, it drags the top layers of water along with it. That moving water pulls on the layers underneath, and those pull on the ones beneath them. In fact, water as deep as 400 meters is still affected by the wind at the ocean's surface. If you zoom out to look at the patterns of surface currents all over the Earth, you'll see that they form big loops called gyres, which travel clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. That's because of the way the Earth's rotation affects the wind patterns that give rise to these currents. If the Earth didn't rotate, air and water would simply move back and forth between low pressure at the equator and high pressure at the poles. But as the Earth spins, air moving from the equator to the North Pole is deflected eastward, and air moving back down is deflected westward. The mirror image happens in the southern hemisphere, so that the major streams of wind form loop-like patterns around the ocean basins. This is called the Coriolis effect. The winds push the ocean beneath them into the same rotating gyres, and because water holds onto heat more effectively than air, these currents help redistribute warmth around the globe. Unlike surface currents, deep ocean currents are driven primarily by changes in the density of seawater. As water moves towards the North Pole, it gets colder. It also has a higher concentration of salt, because the ice crystals that form trap water while leaving salt behind. This cold, salty water is more dense, so it sinks, and warmer surface water takes its place, setting up a vertical current called thermohaline circulation. Thermohaline circulation of deep water and wind-driven surface currents combine to form a winding loop called the global conveyor belt. As water moves from the depths of the ocean to the surface, it carries nutrients that nourish the microorganisms which form the base of many ocean food chains. The global conveyor belt is the longest current in the world, snaking all around the globe, but it only moves a few centimeters per second. It could take a drop of water 1,000 years to make the full trip. However, rising sea temperatures are causing the conveyor belt to seemingly slow down. Models show this causing havoc with weather systems on both sides of the Atlantic, and no one knows what would happen if it continues to slow or if it stopped altogether. The only way we'll be able to forecast correctly and prepare accordingly will be to continue
Currents that we're seeing right now. You can see the one that interests us the most really is the North Pacific currents right here, the gyres here. We have big ones down here in the wide open ocean, right in the Pacific Ocean. All right, the wind fields, like it said in the video, how they're going to go this way and that way, then this way, then that way, depending on Coriolis. So when he talked about, if the conveyor belt stops, it totally stops. Well, I don't think it can totally stop unless the Earth stops spinning. And if the Earth stops spinning, we're all in big trouble. We don't want it to stop spinning. The whole world would flood. In fact, that may be how Noah's flood happened. Maybe the Earth's turned around with the other direction. We don't know. All right, so winds near the surface create waves on the oceans. There are something called trade winds. Consistently blow. They come from the west, are unpredictable. Polar easterlies curve down here at the top and bottom, the direction of the trade winds. Okay, and all of that also affects weather patterns. Okay, so that would contribute to that as well. So if we have Coriolis, we're going to see a turning like this. Now this video, it's one of my favorite videos. But it's really long, and I think I'll just get to the part that is pertinent to what we need, and then I'll cut it short. Okay, so here we go. If you were in physical science with me, you've seen this.
From space, it is clear that the Earth is rotating. However, as an observer on the surface of the Earth, the only indication our planet is rotating is in the observation of the sun during the day and the stars during the night. Every day the sun rises in the east and sets in the west, but we are completely unaware that we are traveling to the east to about 882 miles an hour. Well, why? Well, as you walk north or south from the equator, you are actually getting closer and closer to the Earth's axis of rotation. Because the surface of the Earth is solid, the rotational velocity will decrease as you walk north or south from the equator, because you're actually getting closer and closer to the Earth's axis of rotation. To understand this better, let's imagine that we take the Earth, a sphere, and flatten it out into a rotating disk, like a merry-go-round. If you were to stand on the edge of the merry-go-round, the rotational velocity would be large, and you would feel like you're going to fly off. However, if you stand in the middle, the rotational velocity would be much less, and you would feel like you're barely spinning at all. Now, what if we were to have, and therefore follows a straight path? But because the person trying to catch the ball is still rotating with the merry-go-round, they are quickly moved out of the ball's intended path. Because the merry-go-round is spinning counterclockwise, this deflection is to the right. If it were spinning clockwise, the deflection would be to the left. Now, to an observer above the merry-go-round, the path of the ball appears straight. However, to people on the merry-go-round, the path of the ball curves to the right of the intended motion. This experiment demonstrates how the rotation of the merry-go-round appears to cause a deflection in the path of the ball. This also demonstrates how air movement on the Earth's surface can be deflected by the Earth's rotation, a phenomenon called the Coriolis effect. How do we To answer this question, let's first investigate what would happen to a particle of air that was initially at rest with respect to the Earth. At 30 degrees north latitude, the parcel is traveling to the east with the Earth. But if we were to shove this parcel at 10 miles an hour to the north, what would happen to its motion? We have already seen from the merry-go-round experiment that the ball would be deflected to the right. But why? The answer lies in understanding something called the conservation of angular momentum.
Okay.
Angular momentum
I'm
is
going to stop there because this brings in all the math. And the math would be part of physics class. Okay, and this is not physics class. Okay, and let me tell you what, y'all, if we had a merry-go-round out here in a play, I would totally make y'all go sit out there and roll a ball across it, and you'd see how it just, that's crazy, right? How it just curves like that? Oh man, I think that's nuts. So, anyway, the point being, Have you heard this? You probably heard this, right? When we talk about hurricanes, how the destiny of every hurricane is to turn right. You ever heard that? So it comes to that. So just recently we had a hurricane that hit Florida, right, last week. It came into the Gulf. It built up some momentum because of the warmth of the Gulf water, and then it turned right back onto Florida, right? So it went to the inside of Florida like that. Coriolis is what sent it there. There are also other things playing. Why don't they always go that way? And there used to be in the old days, they thought that Texas couldn't get hit by a hurricane because the destiny is always to turn right. It would always turn right before it got to Texas. Has Texas had hurricanes? Mm-hmm. Some of the biggest ones, right? The biggest one in 1901, the giant one that killed more people than anything else in, as far as a natural disaster, that happened in Galveston, Texas. And then, of course, y'all all remember Harvey? Sat over Houston, dropped 58 inches of rain on Houston. You know, Houston floods with 1 inch of rain. So at 58, there were lots of flooding. We had rain here. I remember that. I think we had, anyway, so we have other things, pressure that builds that causes it to flatten that a little bit to come into Texas. So there'll be different types of pressure in other parts. Like we have this thing called a heat dome over us right now. That heat dome is pushing winds and rain, sadly, away from us. That's why we're not having any rain, because we have this crazy heat dome thing. All right, so the waves. Open ocean waves can carry energy across the sea surface. It's really kind of weird. This is kind of hard to understand. The energy's being carried, but the water isn't. So we think about the water moving through the ocean. It's really moving up and down. That's all it's really doing. It's moving up and down. Okay, let me get this light back on for you. So if you've ever been like to the coast and you go out past the second sandbar or something like that, and you're out there, you've probably noticed you just bob up and down. You just bob up and down, right? It doesn't really drive you enough. There will be something called the tide coming in that will eventually pull you in. But the water itself, the energy is just moving. The water's not, except up and down. All right, so open ocean waves carry energy across the sea surface. They don't actually transport water across the surface.
There's a question that says what would the pressure be for a diver at 132 feet?
Okay, I think that must be a math problem you're supposed to work out. It's supposed to be 14.7 for every 33 and a half feet, right? Wasn't that how it went? Did anybody do that math yet?
Yeah, it's 418.
4 atmospheres? Oh, Lexi did the math.
I just looked at
Well
the
done.
picture. Yeah.
Oh, you looked at the picture. Okay. There you go. Smart. I will try really hard to remember to put my teacher book in so I can follow along with you. I'm blind here. Yeah, I'm just working off my PowerPoint. Yes.
Will there be math on?
Study guides. But I think I avoid math whenever I can. Yeah. Excuse me?
Will it be as bad as chemistry?
No, not even close. Not even close. All right, wave energy. Waves contain energy that is circular. So when I tell you you're bobbing up and down right there, the energy under you is basically in a circle. I'll show you a picture in a second. The energy moves through the wave until it comes to a shallow water, which will cause it to break. Okay, so it's going up and down like this, but when water comes close to a shore, when it hits, it can't make the complete circle. And it breaks the circle. That's what we call breaking wave. All right, so you can see right here, it's all in a circle. The energy's coming up like this. So if I brought in the base like this, I would cut off the bottom part of that circle, causing that to break, bringing waves onto the shore. So it has to do with the topography underneath the ocean that causes the energy to make it to the beach. Okay, it's not the water as much as it is.
Goggles on, and when you go into water, as the wave goes over you, you can see it spinning.
Nice. So I'm going to show you a really cool video here about a guy who tries to photograph that. It's really cool. All right, so breaking waves. Here we go. So see a circular motion here to the right, and as it comes here, that surface underneath, all right, the land is causing that energy to break. And as it breaks, notice what happens. It's wave-like wave. Then all of a sudden we have a peak on it, and a bigger peak, and then we call those broken waves breakers as they hit the shore. All right, so shore waves act differently because they're at the shore. As the water becomes more shallow, the sandy surface interrupts the circular motion, causing the break right here, and enters into what is known as the surf zone. So if you're a surfer, you want to be in the surf zone. Anybody surfed before? I don't have the balance for it. All right, let's just see this real quick here about the waves.
Along with them. They do not. Waves do not transport water. They transport energy through water. If you look at the algae floating in the water, you'll get an idea of what I mean. Notice that as the wave comes through, the algae don't move forward very far. That's because the water's not really moving very far. It's moving in a circle. So as the wave passes through, the algae simply move up and then move down. Now when the waves approach the shore, something a little different happens. The water molecules are still traveling in a circle, but now the molecules that are close to the bottom rub up against the bottom. That causes friction that slows them down. The water molecules near the surface of the water don't experience that friction, so they move more quickly. Eventually, this causes the top of the wave to move in front of the bottom of the wave.
Told you out in the water, yeah. Okay, tides. Is that your next set of blanks? Tides. Tides affect sea life and wave action. They are caused by the gravitational pull on the Earth from the sun and the moon. So we have something called the spring tide. I think that one you're supposed to write down, right? Spring tide is when the sun and the moon are aligned. So we have the sun, the moon either new or the moon full. You've probably heard that on a full moon you have greater tides, right? It's true because they're called the spring tide. All right, so how often per month do we have a full moon? Typically. Once. Now August just had 2, right? And that second one was called the blue moon. They're kind of rare. And also it's a super moon. The moon's kind of closer right now to us, and it's going to result in something very interesting in April when we're going to have a total eclipse of the sun. It's going to be pretty cool. I'll make sure the eclipse coming October 14th, which is on a Saturday. All right, so the spring tide is when they're lined up, causing, if you see this picture in the middle of the Earth is yellow, the blue part is the ocean, the bulge that's created by the pull of the moon and the sun kind of pulling together. Then there's something called the neap tide. The neap tide happens when I do this. The moon is in a 90-degree angle. The sun and the moon are aligned so that the Earth has lower tides than normal. Okay, so they're kind of in a turn there. So if I go back, you can see here and here, the midway part, top and bottom there would be 90 degrees. That ends up with a neap tide. All right, so what we'll have is 2 spring tides per month on our new moon and our full moon, and 2 neap tides per month on our first quarter and third quarter. All right, did everybody get a little something? You understand what's going on there? Here's that other picture showing that the tide isn't quite as big here on our neap tide. I told you I had lots of videos today.
If it weren't for the moon and the sun, there would be no tides. Now in this animation, I'm going to concentrate on the moon because its effect is the greatest. Without the moon, the waters in the ocean would be distributed rather uniformly around the Earth. But as soon as you put the moon in the picture, its gravitational force changes things. The moon pulls on the ocean water, causing it to bulge out. It also pulls on the Earth, so the Earth moves towards the moon as well. This makes the ocean water form essentially an ellipse around the Earth. So if we were looking down on the Earth, this is essentially what we would see. Now let's consider a particular point on the Earth illustrated by this house. Now remember, the Earth rotates a full change much because it takes 28 days for the moon to get around the Earth. So in the end, we can assume that the moon doesn't move very much during an entire 24-hour day. So what happens as a result of the Earth's rotation? Well, look at the house now. It's sitting in an area that has a little water, so it's experiencing low tide. As the Earth rotates, however, it starts rotating into an area with a lot of water. When it finally gets to the point where it's reached the maximum of the water, it's experiencing high tide. As the Earth continues to rotate, the house once again gets to the point where it is experiencing very little water. That's low tide. As the Earth continues to rotate, the house once again experiences an area of high water, so it's now experiencing high tide. Of course, to complete the day, the Earth would continue to rotate, putting the house back to where it experiences low tide again. Tides. That's why in most regions of the Earth, in most seasons, every place will experience 2 high tides and 2 low tides in a 24-hour period.
All right, that's a good question right there. How many high tides do you have per day? 2.
Oh. 2 in the morning.
One in the whatever. It depends on where you are. And they'll tell you exactly what time high tide will be, or where you go somewhere. Also, the depth of the tide or the intensity of the tide depends on where you are. All right, so here we go. Remember the neap tide and the spring tides, those are per month, right? So we have the 2 neap tides per month and the 2 spring tides per month, depending on the moon here or the moon there, right? But daily, because the earth is spinning, that's a different function, right? Then you will experience high tide, low tide twice a day. And in one place in the world where the tide is tide in the world, in other words, difference between low tide and high tide. One of the smallest is the Mediterranean Sea, because it's so enclosed. There's only a little outlet there called the Pillar of Hercules right there at the Gibraltar. There's only a little bit of water coming in and out through it. So the tide between high tide and low tide in the Mediterranean is something about 2 inches between low and high tide, right? So you don't notice it very much. So sailors didn't have to deal with it all that much. But if you go down to the ocean, the tides are going to be much more affected because they have room for it to go. And it happens because, see, it moves up into this channel right here of Nova Scotia. It is affected very, very dramatically. So this is high tide. Look at low tide. Look at those ships on top. Look where they are. They're touching the ground because there's no water, because it's low tide. So those sailors can't even go out at low tide. They have to wait till the water comes in. I have another video. Yeah. And then I thought I showed you the land. It was really cool, the land. This will show it, I guess.
Just as currents move the waters of the world ocean, so do the tides, which ebb and flow under the gravitational pull of the moon. High tides follow the moon as it orbits the earth. Canada's Bay of Fundy on the Atlantic coast is famous for its immense tidal flow. Up to 1 trillion tons of water enter and leave the bay with each tide. Coastal channels leaving veins of red mud. The tides enrich the land enriches the sea. While the moon's gravity tugs.
Yeah, that's all we're watching. I just wanted to see the Bay of Fundy change like that.
I'm using my phone to go swimming in moonlight or something. That'd be weird.
Or else take a nap. Okay. All right, so let's talk about turnover now, or overturn. Is there something next and then overturn comes after? Or do I have something out of order?
Yeah.
The water layers of columns.
Okay, so skip down to overturn. Okay, but so let's go down. We'll come back to that thing. You're going to end up drawing something, I think, in that box. So let's go down to turnover. We're going to see. We're going to look at it on the context of a lake because it's a little easier to grasp because it's a smaller area, so we can look at it. All right, so we're going to see there are layers. With those are the ones you're going to write down in just a minute. And what happens is that the temperature changes as it gets to the surface. As it gets to the surface, it actually cools down because wind is blowing across it. Okay, we have some evaporation. When there's evaporation, we have it cooling. You think about this time in Texas, if anybody has a pool, you know that top surface is actually very hot, right? Because the sun's been shining on it. So things change a little bit in this super, super hot weather. But in a large body of water, they tend to cool off the top with the wind that blows across it. And so therefore, if it cools, it's going to drop down, therefore pushing the stuff down up to the surface, and we have movement. Okay, and it's important to have the creatures living there. Okay, so you can see it's pushing the cool stuff, the wind here, blowing across. It's pushing it down, pushing these guys up like this, and we'll have that mixing of the water known as overturn. Does it bother you that I have this many videos? You're real cool with that? Y'all good? I don't think I have them in every lecture. Just this one happens to have a lot.
Cool temperatures at the ocean surface cause the surface water to become cooler. Since cooler water is more dense than warmer water, as the water cools, it begins to sink. As the water sinks, it displaces an equal volume of water in the deeper layers of the ocean, causing that water to move upwards. This process, called overturn, benefits the ocean. The surface waters are rich in oxygen. As the cool surface waters sink then, oxygen is brought to the lower parts of the ocean. The waters in the lower parts of the ocean move upward. That brings nutrients up towards the surface of the ocean.
All right, nice and short. All right, here's the thing I believe you were labeling. So you go back above that a little bit right there. The general ocean layers are the surface layer. We're going to spend a lot of time on that. It's known as the epipelagic zone. We're going to see a lot of the creatures of the ocean live in that zone. Then we have something called the thermocline. So thermo meaning temperature, cline meaning up and down, right? So it's changing. And then our deep layer, all right? It's also called the water column, and overturn in the water column is essential for healthy oceans. And you can probably notice on the ocean we're going to have a lot more wind, therefore a lot more cooling at the surface, even near the equator. So as far as I know, I think you're supposed to be writing surface, thermocline, and deep. 3 layers, right? And you're drawing the picture? Yeah? Okay. Yeah. I'll give you on the next slide, I'll give you the depths. Although they have them here, don't they? This is in meters. I'll give you feet in a minute. So the epipelagic goes down about 200 meters, thermocline between 200 and 1,000, and below 1,000 is the deep layer. We're going to see some changes in temperature, changes in light absorption, changes in salinity, all these things working to keep the thing moving.
We have to draw that.
Would you rather draw that one?
Yes.
Is anybody still working on this one?
Yeah.
It's really the same. All you have is this thing to low. So here's the temperature scale on the bottom. Warmer, colder. All right, and cool, as the cool comes across here, will cause it to drop, making this cool stuff climb a little bit up the thermocline. But you can draw that other one if you like, Zoe. Okay. It's a little darker. I'll turn the light on. Also remember, I'm recording this. So if you want it, let me know. I'll send you the link. You can watch it on YouTube.
Hey y'all.
Feet. So there's our feet. Remember we said 200 meters, 660 feet. And then we have our thermocline too, right here. So we have our top, and then we have this layer here, and then our deep. So that's 660 to 5,000 feet. And over 5,000 feet gets down into the deep layer. Mesopelagic, bathypelagic. Did I get those mixed up? One of them's bathy, one of them's meso. Oh, abyssopelagic, yeah. This is mesopelagic. Epipelagic, mesopelagic, bathypelagic, abyssopelagic. Named after the abyssal zone, right? So in the thermocline we have a serious change in temperature. We get to a point down here where it doesn't get colder. It just stays a general cold temperature. All right, here we go. Ocean motion is vital, meaning it has to keep life going. What would happen if the ocean were still?
Algae.
Overgrowth, right? So there'd be some stagnant water and life would be challenged. No nutrient or oxygen mixing would take place, therefore organisms would eventually die. Weather patterns would cease. We'd have trouble there. And plankton would die, creating oxygen depletion. All right, just because they're not getting the nutrients that they need that come from below. So these are 3 answers to that question. What would happen if the ocean were still? They're important. They are the #1 providers and generators of oxygen that we breathe. People think about the rainforest, but it's really the plankton that we have to take care of. It's really those photosynthetic algae and even the blue-green algae, which is a bacterium.
Isn't it like 60% of the world's oxygen also comes from ocean?
It's more like 80 or 85.
But plants? Or
Well, ocean plants, including algae, if you put algae in that group, even though they're in a different kingdom, yes.
Which, I mean, because obviously there's a lot more ocean than forest, but which one produces more oxygen per, like, amount of space?
Ocean.
Ocean.
Yeah, definitely. The plants are somewhat limited. But I still say let's not cut all our trees down. I wouldn't want to cut all the trees down. But we really Okay, we have a problem with trash. So since it's making those big round circles like that, actually trash gets collected up. Now this is an over dramatization. It doesn't really look like that. In fact, the Great American Garbage Patch, or excuse me, is it American? Yeah, American Garbage Patch. It doesn't look quite like that. That's disgusting, obviously. We've got some trash collecting there. That's probably in a river or something. I just wanted to be a little dramatic. And just to show you that indeed we do have, just like those little rubber duckies went around. Well, so what happens if they get caught in that gyre like that, they'll end up sort of in a region. And they're floating right outside the western United States. And trying to clean it up is more difficult than you think. Well, I could go in here and scoop it up with something or something like that. It gets to become what is known as microplastic. It's very dangerous.
Well, those two
Okay.
patches in the Atlantic Pacific, now there's life growing on.
Because there's enough there. Life will prevail. That's for sure. We know that from the fires. Okay, I'm going to show you this really great video of a guy who makes a living photographing waves. Because we were talking about waves today. He's in Hawaii, and I actually looked up his art yesterday, and it's really amazing. But he's a little bit crazy.
I think it's basically.
All right, so here we go. This is just for our enjoyment.
It was for that.
For me, I didn't plan to be this wave photographer. I went out there because I love the shore, and that's cool, but I'd rather go out in heavy shore break with nobody out and capture some heavy four-lipped monster throwing over with the sand sucking up. I have such a good time. This is Waimea Bay. This is my stomping grounds. When I was a kid, I came out here with my brother and we body surfed, and then one day I decided to get a surfboard and actually surf the shore break. Just got this killer vibe and feeling, and just making it down these big shore break waves and pulling in, and just getting that feeling of deep inside a tube and traveling, and it's just something I had a passion for, and I still do to this day. Now with a camera instead of the surfboard, I just capture these moments. My wife came home with a picture of a wave of Waimea shore break. I'm like, honey, don't bother buying a picture. I'll get ST500, and I got this thing from. It would go over a big shore break wave, boom, and finally I could time it. Like, okay, it's right here, jacking up. Hold the trigger, it'll click right when the thing comes over. Showed it to my brother and my family, like, wow, that's different. It was weird how it just kind of evolved. I threw my work out there, with technology. And some companies, this one in the UK, sent them my favorite 20 images, and they said, okay, we're going to run it. I thought nothing of it. We're going to run it. I went to bed. I woke up 700 emails. Good Morning America, Today's Show, Inside Edition, all on the phone, just trying to negotiate to get me up to New York for the next morning show. I'm like, are you joking? I was like tripping out. 8 years ago, I didn't have a camera. I just love, it's just all about being out on the shore break and getting that shot. You ask, well, what's your settings? How did you promote yourself? I guess people feel the passion, I think, in the art, in the waves, like the backwashes, the beauty, 110%, 6 hours a day. That's my preference. There's some dangers involved with shooting, a large shore break. I've got sucked over the falls and smashed into the sand. I've separated my shoulder. I've had the housing bit my head, and boom, you get slapped in the face, and you get tossed up the beach, and sometimes you have a couple of friends, and you're yelling and having it's fun, dude. The worst thing for me, like the fear-wise, is just, not making it up, just wave after wave and not being able to breathe and trying to hold your breath, and then another big wave's coming and you're stuck and you can't get in, you can't get out. That's the moments where I feared for my life. I don't like that, you know what I mean? It's a spooky feeling. But then you get that perfect shot, if I ever stop enjoying it, which I don't think I ever will, but then I can kind of step back and chill a little bit, but I'm a pretty hyper guy, and I'm ambitious and love shore break, and that's my baby,
Okay, a little bit crazy, yeah. He's in Hawaii, and they have tremendous waves there. So much so they say when you're in Hawaii, never turn your back on a wave. You got to see it coming, all right? Otherwise, it'll get you. So I was there, and there's a part of the beach, and nobody was there, right? I said, to my husband, I said, let's go over this part. Nobody's there. We'll go. Well, it was because the waves were so violent, and I didn't know that, right? So I go over and I was like, this is terrible. I'm gonna get out. So I'm trying to get out. I'm walking away to get out, right? Well, I turned my back to the wave. Well, it got me, and it had me just boom. but slamming me against the sand. And I'm thinking the whole hard on my husband to get my body back to Texas, you know, because I thought I was dead. I thought it was over. And it finally spit me out, like Jonah in the whale. I was like, oh. And I said, I'm not getting back in. I said, I'm done. I'm just going to watch it from here, you know. So anyway, this guy sells his work. You can buy it. I think this is one of his famous ones here. It's beautiful, obviously. And I saw, like, you know, you can buy a print for $50 or something like that. He does animal life as well. Here's a turtle. No, I think now I must take this one. I think is one of the famous. But it looks like that first one, right? With the sun coming in, just beautiful. All right, it's lab time. We're going to work a little bit with Coriolis effect. I'm going to turn this on.
I don't know, there's one blank that I didn't